got a twinge of sadness when I saw my old coworkers the other day, and I loved working with Dob. He was really great to work with. just do it. It was great.
So fair warning.
Yeah.
I'm going to start recording, which will record your audio.
Huh, okay. Thank you for the.
I think that it's done well.
You're gonna record me chewing. All right.
The issue is. Yeah, so you're using healthcare, electronic banking, contract, public email. The card, check stores, your full name, partner.
Thank you for the pizza.
You're welcome.
Sure. Hand washing station.
Yes, you go through here and then to the right.
Okay.
There we go. Cool. Hey, he's got some free tickets. Jake, I will sign Jake up for giving free tickets away.
We have a limited number of free tickets, but first come, first serve.
Unlimited number of free tickets.
What's that? For B-sides. Tickets for B-sides. It's a.
BSidespgh.com.
He's-
You go to bsidespgh.com, you can see it's a security conference that happens on July 11th at the casino. So we can talk about that afterwards if you're interested. We've got Jake here. Talk about Red Team Road Rage, I guess. I think of this as driver exploitation on Windows. There's a lab portion to this, I believe, right? Still? Okay. And so in order to do that, you need an AWS account to follow it exactly the way that it's set up. I have a bunch of $20 credits for AWS. So if you have like a personally funded AWS account, I could throw you $20. You just have to like somehow message me and I'll send you a little code that you put in and you get $20 off. So that's because I'm an AWS community builder and they give me like 100 of them a year. So I have to use them or they won't keep giving them to me. So please take them and use them. What else is going? Oh, thanks to Alex and the Hacker Guild for the food, the drinks. Yeah, let's give them a round of applause. For the food and the drinks and the location, power, AV, all this great stuff. So I appreciate that. This is being live streamed. This part is not because it's on his microphone unless we can pick it up from over there. But once he starts, that'll all be recorded and we're going to put that on YouTube. It's live streaming on YouTube. We've got a couple people on right now already. So if you miss anything, you're going to go back. That'll be recorded. Did I miss anything? AWS account is important if you're going to participate in the hands-on lab. Spin up an AWS account. And do you want to say anything about this finding orphan and abandoned wells? There's a public meeting here on July 15th. Yeah.
No, I don't.
Okay. So everyone's invited. Bring your kids. I'm just kind of reading off this pamphlet. These are these flyers are over there as well. Learn more projects, technology, eat food and drink things, which is one of my favorite things to do. And there'll be some giveaways as well. So this is PDF.org is the website, and this is flyers we can learn more against July 15th. And what else? I said B-sides. I talked about Jake. All right, let's just cut to Jake. Give Jake a one round of applause. Jake Mayhew. Going to give a presentation on hacking Windows boxes.
Okay, cool. Hey, everybody. My name is Jake. And we're actually not going to start off with this just because we're going to spin up a Windows box. I don't see a ton of laptops out here, so that's okay. You don't have to follow along. I'd recommend it, but you don't have to. But we're going to do this because I know there's a couple of people on the on the stream. And so if anybody's interested in following along, we'll go through this kind of slowly and methodically to set it up. And then we'll do some talking and go through some slides. And then after that, we'll go back to the lab once it's kind of all spun up and everything like that. And we'll do some playing around with the Windows kernel, which will be a lot of fun. So yeah, this is going to be a variation of a talk that I gave at NorthSec in Montreal a couple of weeks ago. I focus more on the EDR side of things with the talk. I'll kind of gloss over some of that and focus more on the exploitation piece because, like John was saying, I submitted a talk to B-Sides about like driver exploitation and kernel exploitation and how it's beneficial for red team operators. And so I kind of wanted to focus a little bit more on that. So excuse me. But if anybody wants to talk about anything that I kind of gloss over, you're always welcome to reach out to me and we can talk as much as you like about it. So real quick, if you're following along, all we're really going to do is set up one server in AWS. It's going to be a Windows Server 2019 for various reasons. And then we're going to install some tools onto it and so forth, just so you kind of know some of the tools of the trade and so forth. This guy was terminated because it was too small. We're going to create a new server. So you can just go into instances, add a new instance, and do Windows Server 2019. So Windows Server 2019 is a little bit old right now, but it is certainly still found in a lot of environments. And it's just nice because it doesn't have all sorts of brand spanking new kernel mitigations that have been introduced over the last, 2 or 3 iterations, 2022 and 2025. Similar to kind of like mitigations that have been rolled out for Windows 11 as well, which we'll kind of talk about a little bit later. As we're kind of getting started here, does anybody have, I'll just put it really broadly, binary exploitation experience? So one, okay, and there's no requirement for that. I just want just a little bit of context so I don't like run past things that are maybe we could spend a little bit more time with. So
does the instance size matter? It's how you pick too large the family. Like
yeah,
if you pick like a Graviton instance, would that be a problem?
I like large. I'm sure you could get away with something else, but just for a server instance, I'm gonna do 8 gigs of memory.
Family doesn't matter if it's like a T4G or...
No, it doesn't really matter. I'm not a huge AWS guy, so I don't know all the differences between the different families and stuff like that.
It's really just the cost. Like
yeah.
Labs. Like I mean, if you have the credits, it doesn't matter. But
yeah.
T2s are more expensive because AWS wants people to get away from them.
Okay, gotcha. Yeah, I just use T2s, but if you want to use something else, all you really need is 8 gigs of RAM, and that's really it. That's really about it. So yeah. Okay, so you can create a new key pair if you'd like, which we will use to decrypt the administrator password. And then we want to allow RDP traffic from anywhere because we're going to YOLO it. And we want at least 50 gigs on our storage. It's going to default to 30. We want 50 because we're going to install Visual Studio. And it's beefy, even if you're just installing one little thing of it. So okay, so that's running, and that's pretty much all we're going to do there for now while it's getting set up. Here you see some instructions for the setup portion. So just to give you an idea of what we're doing, setting up Windows Server 2019, and then we're going to download a few things because it's still a little bit older. We're going to have to install Edge because it's got Internet Explorer on it, and then we're going to install WinDebug and Visual Studio. WinDebug is to inspect memory and to make modifications. You can do it in user mode or in kernel mode, but we're going to use the kernel debugger for Windows WinDebug. It's kind of the de facto at this point. I don't know anybody that uses really anything other than WinDebug, but I'm sure there's options. And then we're going to test kernel debugging and just kind of get it set up. And so talk a little bit about what's involved with kernel debugging and some of the gotchas there. And then we're going to enable it by doing debug and test signing mode. So yeah, question. Yeah, we're going to get to that in the slides. So yeah, thank you. Yeah, we will talk about kernel mode. And so if this is like, I know at least for me, up until I started really digging into this kind of stuff, if I heard kernel mode, I would just kind of put my blinders on, or like it can be kind of a scary concept to really think about. But we'll try to demystify it a little bit. It's unfortunately it takes a lot of a lot of playing around, a lot of studying, a lot of experimentation to really feel comfortable with it, at least in my experience. But we will talk about it and hopefully, give a little bit of intro and so forth. So, yep, good question. So we're going to enable debug and test signing mode, and then we're going to download a vulnerable driver. We're going to talk about what drivers are too, and from a vulnerable driver repo, and then we're going to install it and set it up so that we can exploit it. And if all of that is confusing or scary, we'll hopefully kind of do it pretty methodically and slowly so that it at least is easy to follow, if not, super clear. So, okay, so if you're following along with the labs, hopefully your instance is being set up. It probably is you're probably able to log into it at this point. But yeah, so like I said, I did this for a different talk, so I'm going to kind of tailor it and blitz through a ton of things. So I'm going to kind of skip intros and all that kind of stuff, but we're going to talk about weaponizing vulnerable drivers, and we'll just say kernel exploitation in general for red team purposes. So what really got me interested in this topic is I've worked in offensive security for the past 7 or 8 years, and I started with like the OSCP and stuff, which some of you either heard of or have taken before. And in the OSCP, there's no defensive controls whatsoever. So you're just on a box, and there's no AV, no EDR, no network controls, no nothing. And it's just vulnerabilities that you can play around with. And so that was a lot of fun. But then when you get into the real world and you're fighting things like CrowdStrike, SentinelOne, modern EDR, XDRs, I got my butt kicked basically, because you're like, oh, you want to upload a payload or whatever you're doing, and it just gets scrubbed. And even if you're doing living off the land type of attacks, it's going to get knocked off, or you're going to get knocked off systems and so forth. Excuse me. So I got really annoyed, and that led me to seeing how we could subvert the controls of EDRs. And most EDRs, well, actually pretty much every EDR at this point is going to have a kernel driver. So basically a way to get code execution in kernel mode to be able to gather telemetry at the lowest level of the operating system. So that's how EDRs get such great information. Many of us are pretty well aware at this point, after July of last year, that EDR vendors use kernel drivers because the world stopped for a little while because CrowdStrike pushed out an update, right? And they pushed out an update to csagent.sys, which is their driver. And then it was updated. The code was actually a channel file was, but I won't get into that. Basically, the code running in kernel was updated, and then there was a bug in it. And when you're in the kernel land, there's no error checking. There's no well, there can be error checking, but there's no error recovery. It just crashes the system. And so CrowdStrike and other EDRs load early on in the operating system boot cycle. It's called an early launch anti-malware driver. So it's loaded early in the cycle and the boot cycle to be able to prevent stuff like rootkits and so forth from being loaded. And so it will load early. And unfortunately for CrowdStrike, it crashed early. And so you loaded it immediately and it crashed, and then you rebooted and then it crashed, and it rebooted and then it crashed. And so the world stopped. And that's just one example of how powerful kernels or the kernel drivers are, and these various components that EDRs will implement. So I guess I didn't really skip over the intro. That's kind of the intro. But anyways, so what's cool about kernel drivers and kernel exploitation is you can use it, for instance, a vulnerable driver, like what CrowdStrike had. You can exploit a vulnerability that's in a driver to be able to attack the EDR telemetry itself. So here's just a splash screen of a bunch of different news articles from CrowdStrike, SentinelOne, ESET, different places where attackers and threat actors are starting to use these bring your own vulnerable driver attacks, where they're finding a vulnerability in a driver that's not on a system. They're bringing it onto the system, loading it, which is what we're going to do today, and then exploiting it to then remove telemetry from a EDR solution. And then they can essentially do your OCP stuff, so to speak, uninhibited. And so, you see there's something on the bottom right there called Terminator. So what Terminator did is it was a driver that when loaded, you could send a code to it with a process ID basically, and then it would kill that process ID. So you just find, oh, hey, where's the CrowdStrike process? Where's the Defender process? Whatever. And then send that to the driver, and then it would kill it. And because it's coming from the kernel mode, essentially it's completely trusted, and it will kill whatever you want it to kill. So yeah, that's just one example, but a lot of threat actors, more and more and more, are using this type of attack because it's just so annoying to fight these really good EDRs. I have to hand it to these EDR vendors that are doing a really good job in protecting endpoints these days, at least on Windows. They're not so good in Linux and Mac at this point, but at least in Windows, they're pretty good. So defenders do what defenders do when there's a new suite of attacks and they have an LOL project, or living off the land project. So there's like lolbins, which is living off the land binaries. So things like, sysinternals tools and all that kind of stuff that attackers have been using for malicious purposes that aren't strictly malware or custom malware. This is just the driver's version of the project. So it's a repository of like a whole bunch of known vulnerable drivers. Like, hey, that driver that I mentioned that will terminate arbitrary processes and so forth. It would have an entry there, and then attackers, or rather defenders, could go to this project, reference that, and start blocking these drivers from being loaded or flagging them and so forth. And so the one that we're going to use today in our lab is going to be is a pretty well-known one that's in this project that we're actually going to download from this project. And so while it's going to work on our system without any EDR, if we load it onto like a CrowdStrike or something, it's going to get blocked from loading, or at least alerted, and then it might even block some malicious activity because it's just so well known, essentially. So anyways, this is a little bit about me. I'm the director of operations, offensive operations at White Knight Labs. So I do a lot of R&D. I do some teaching and stuff, and yeah, that's about it. Okay. Well, I try. So yeah, you can kind of ignore the contents, and because we're going to gloss over a lot of this. But for the next portion, we're going to talk about user mode versus kernel mode. So we can dive into that a little bit more, because if it's not really, if you're still like, as I'm talking, you're like, I still don't get what kernel mode is, that's fine. We're going to talk about it. And then we're going to talk about exploitation, particularly for EDR evasion, and the different types of kernel exploits that are valuable for this purpose, essentially. And then we'll do the demo at the end. So this is a masterfully artful slide that I came up with. Actually, I didn't do the one. So the only pretty thing on the slide was something that I didn't do. But this is just a quick OS architecture review. So we have different rings. If you're familiar with that terminology, ring 3 and ring 0 are the two that are typically used, but different operating systems might use different terminology. But with Windows, there's pretty much two modes. There's user mode and there's kernel mode. And user mode is referred to as ring 3, and then kernel mode is referred to as ring 0. So ring 3 is user mode, which is pretty much everything that you and I would do on on any operating system. Just focusing on Windows here. So logging in, sending emails, browsing the web, and any administrative activities as well. So if you're installing software, if you're troubleshooting, if you're running PowerShell, pretty much everything you're doing, at least when you're interacting with it, is going to be ring 3 or user mode. And then ring 0 is kernel mode, or pretty much everything that is happening transparently under the hood in Windows. So that's like memory management, it's scheduling, like which thread is being run and which instructions being executed at which time. None of us want to code a scheduler. It's not fun things to schedule, at least I wouldn't find it fun. TCP/IP, so actually making that connection and dealing with the packets and constructing them, deconstructing them, and handling that data. All of that's happening at the kernel level, and any type of hardware interactions, right? So if you, I like to use the example of the Nmap driver, because many of us have at least played around with Nmap before, to send a SYN scan that interacts with the networking stack in a very odd way. So normally, you're going to send a request to the kernel and say, hey, make a connection to this port on this system. And the kernel is going to do that for you. And it's just going to return essentially a reference or a handle to that connection. That's the normal operation. But in a TCP SYN scan, you're just sending a SYN packet, which is abnormal, very rare behavior that is pretty much only used in a SYN scan, essentially. And so you would have to install a driver to be able to implement that specific functionality, to do that weird thing. And so drivers are a way that the kernel allows for a third party to do something in that privileged core of the OS. So I like to think in terms of web APIs for this as an analogy, because it's usually something that most of us are at least more familiar with, as opposed to kernel mode and user mode. But if you think about like in terms of a web API, you have a client and a server, and the client's going to send a request to the server, and it's going to say like, hey, I want to log in. And so it's going to send a request to a specific URL, and it's going to provide arguments of the user, password, session data, all that kind of stuff, headers, etc. And then on the server side, it's going to log you in. It's going to check you on the backend database. It's going to do whatever checks it is. It's going to assign a cookie if you're successful and so forth. And then it's going to, it's going to return a cookie for your session authentication. That's the result of it, so that you can track your state. That's pretty similar, or at least a reasonable analogy for user mode and kernel mode. The user mode is the client. It's making a request. You're gonna give it a syscall number, saying like, hey, I want to allocate memory, or I want to make a TCP connection request or something. And you give it the arguments like, hey, I want to connect to this port on this system. And then you send the syscall, which is like the URL. And then it's going to make that connection transparently to you as the client or user. And then it's going to return a reference to that, in this case, this connection, so that you can interact with it. You can send and receive data. But you don't see, as the user, any of that TCP interaction, like the SYN, the SYNAC, and so forth. So another visual I like to use is on the right here, is kind of tracing how code gets executed between the kernel and the user mode. If I have up here an example of I like old N64 games because that's what I grew up playing. So if you have a N64 emulator executable that's running, it's going to run a Windows API, like create a window to be able to display the game. And it's going to eventually reach a DLL that's going to have the syscall to open up a window to display it on the screen. But it's not actually going to do it in user mode. You're going to send a request that's going to go to the kernel, and it's going to say, hey, open up a window that's this size, that has these properties, this window title, and so forth. And then it's going to transition to kernel mode that's actually going to implement that in the hardware and in the graphics and so forth. Actually uses other drivers besides just the kernel, but this is a good visualization of it, so to speak. And so the kernel is going to actually create the window, display it on the screen, and then return a handle to the window back to user mode. So if you want to close it or you want to do something with that that window, you can do that. So that's just a quick crash course on user mode versus kernel mode. Just a little bit more is in kernel mode, I've alluded to the term drivers versus kernel, and I've used those two terms kind of interchangeably. The kernel is actually this NTOS kernel.exe. If you've heard of that before, that's actually the kernel image that implements like all the memory management and all that kind of stuff. But if you have something related, like say the TCP driver or the Nmap driver or something that you're going to extend the functionality of the kernel, that's going to be a driver, which is typically a .sys file, which is the same file format, but it's kernel mode code that's being loaded. And so like if you have, I'm just going to keep using the Nmap example. If you have Nmap and you try to run a syn scan, but you don't install the driver, it's going to fail. And so you have to install the driver so that you can interact with the driver to be able to do that custom functionality. So interacting with these different components, the kernel is typically syscalls and callbacks. So syscall is like, hey, I want to create a window, and then it creates it, and then you get a reference to that. A callback is something that you have a certain action done on a specific event. So for instance, you might have a process being created, and then there's certain code that should be run whenever a process is created. So that's the kernel. Kernel drivers actually have something called an ioctl, or an input-output control code, where you can send a buffer of data to, for instance, you can send it to the Nmap driver. Hey, I want to connect to this system and do just a syn scan, and then you can tell the Nmap driver to do that, and it will do it from kernel mode. So I know a lot of this is probably a little bit boring or maybe a little bit overwhelming, but this is just kind of the fundamentals of kernel attacks and exploitation. Go for it. Yeah.
Can you talk a little bit about, like, is there eBPF? Are you familiar with eBPF?
I've heard of it. Yeah. Yeah.
Okay. Do you know how that like intersects with any of these concepts? Because eBPF is typically a Linux technology. So
Yeah.
I know they ported to Windows, but I don't
Yeah.
know how it interacts with the Windows.
So eBPF would be, that's Berkeley packet filter, right?
Standard Berkeley.
So is that a way that you can filter packets, almost like a firewall type technology?
eBPF is used for basically extending the kernel.
Okay.
So
Yeah.
you can write small C models, and we will be attaching the kernel and we'll be doing more stuff. So in Linux land, you can use, if you want to make an EDR, so
Yeah.
eBPF will be a good way to manage an EDR, manage a firewall, because you will be doing it on the kernel level.
Okay.
Yeah, you could do things like callbacks, like the way you explained it. You essentially can hook system calls in the kernel, and when that system call is run, you run your arbitrary code.
Okay,
and so that's
gotcha.
where EDRs, can get really good telemetry, but you can do anything like measuring like observability and things like that. I just wasn't sure. I know that they have a project where they ported it to the Windows kernel, but I wasn't sure exactly how it works, other than I watched an hour-long video once where they talked about mapping Linux system calls to Windows system calls and how much of a nightmare it was.
Yeah, I believe it. It sounds very similar to the type of stuff that EDR drivers would do on Linux, or on Windows, that we'll kind of briefly touch on, like the callbacks and so forth. And I'd imagine that a Windows port of eBPF would be like some combination of this type of thing. Yeah.
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 Microsoft.
Yeah. Well, if you see it, send it to me. I'll dig into it. I'd be interested.
Yeah, Microsoft has a project called eBPF for Windows.
Okay. Okay. I'm sure there's a driver component to it that essentially implements a lot of the telemetry, and it's probably a layer that enables you to write modules and so forth and kind of customize things. So definitely would be interested in learning more about that. So.
Sorry, one last question on that. Is there, in eBPF, there's the idea of the virtual machine that runs in kernel mode. Is there any sort of parallel concept in Windows where you can run your arbitrary code in the kernel? That doesn't require a reboot.
That doesn't require a reboot. Usually, so in general, Microsoft is extremely protective of its kernel, and so some of the problems that we'll run into with some of these attacks is essentially you can't just write a kernel driver and load it into Windows, because it's going to be unsigned. So Microsoft requires all kernel mode code to be signed. And it's even implemented certain features like one's called HVCI. So it's hypervisor protected code integrity. I think that's what it's called. But anyways, it's essentially ACG for the kernel, if you've heard of ACG. So it's basically saying like you can't have a executable or a writable portion of a writable page of memory be turned into executable. So you can't just like allocate some code in the kernel and the mark it as executable or change the permissions in that sense. And so essentially everything in the kernel has to be signed. So at least with like, this is like Windows 11 to current, so more of the very recent stuff. But since, I don't know, Windows XP, SP3, I think, they've had driver signature enforcement, which basically requires every driver level code to be signed. You can like inject code into the kernel if HVCI is not enabled, but like it becomes, it's all exploitation scenarios in that sense. Yeah. Right. So if there's like an approved method, it's like Microsoft wants you to submit your code to them, have it be signed, and then load it. So they kind of make it as difficult as possible to do that because they just want to protect their kernel. So yeah, great question, and we'll probably dig into that. So if you want to ask more questions, this stuff comes up too. Any questions on the before we move on? Any questions on like the architecture review or anything? I know we condensed like maybe a 4-week class into that. So go ahead.
The EDRs nowadays, are they using AMZ?
Oh yeah. AMZ is huge. So AMZ, for those of you guys who are not, excuse me, not familiar, it's the anti-malware scan interface. So it's a way to essentially scan scripts and so forth. So you can scan VB script, you can scan PowerShell, and you can scan things like even like .NET code and so forth. And it's typically, it allows EDR vendors and antivirus vendors to hook into it. So it's like a extendable, so to speak. So like if you're CrowdStrike, you can have like a custom AMZ provider and stuff like that. So pretty much all of them use it in some way, shape, or form to get telemetry and to get insight into the scripts that are being run. So you're going to have like a PowerShell process, but then you have all of this stuff that's happening within the PowerShell process that can't easily be tracked without something like AMZ. So yeah, they're definitely using that. AMZ is typically more in user mode just because of the way it works. Excuse me, although it's enforced in the kernel mode. Although I'd have to dig into that a little bit more. But yeah, they're pretty much all using that in some way, shape, or form. But like if you're a bigger EDR vendor like CrowdStrike, you're going to have like a custom AMZ provider and stuff like that. Although CrowdStrike's AMZ isn't awesome, but it's different, which makes it a little bit more like it requires a little bit more work. Go ahead.
I have a question.
Yeah.
If you're exploiting blocks and you've got system on
Yeah.
the box, so you're still running in user mode. You're not really kernel mode.
Yes.
If you have the system, so you still block.
Yeah, we will get back to that when we get into the lab. So we're going to do that. Yes. So the quick answer is you are doing something in kernel mode through your exploit to impact your privileges in user mode, if that makes sense. So you can do more things in kernel mode, but when you're running code in the kernel land, if that's how your exploit works, you don't have to run code, which is what we're going to talk about tonight. If you're running code, it's going to be usually a very short stub of like shell code to like copy a token or something. And then you're going to copy it, and then you have it to your exploit process or a future process or something. And then you can get system or whatever. But usually the code, if you're implementing code in the kernel land, it's usually like a rootkit type functionality where if you want to like hook things and get inject into like early on in the boot process and bootkits and rootkits and stuff like that. For me, in like the offensive security type stuff, I don't care about rootkits as much. Like I don't want to, hook into your crypto keys or anything like that for long term. It's usually I'm looking to grab a password or something like that, or to get some like a Cobalt Strike beacon or something like that past the EDR. So. Yeah, we'll come back to that. So a couple of things go ahead.
The last year CrowdStrike blue screened a lot of machines. And then Microsoft had the secret meeting with the EDR vendors.
Yeah.
Did anything ever come out of that? Did they? Because that was kind of this conversation.
Mhm.
Right?
Yeah. So after, yeah, they had a lot of attention to it, as you mentioned, and then I think it was like the Falcon, like the CrowdStrike conference, or maybe it was the Microsoft conference. I can't remember. They had the CEO of Microsoft come on, and he hinted strongly at them trying to create some sort of like abstraction layer between user mode and kernel mode, so that EDR vendors aren't really running code in the kernel, because now that makes everybody kind of cringe, because they don't want a Delta scenario where all their systems are down because some auto update did a CrowdStrike. So that was something that they talked about. I have not seen anything meaningful being released, and it probably would take a long time. And it kind of makes my mouth froth a little bit because, or my mouth water a little bit, because I'd imagine once they release it, there's going to be a lot of interesting vulnerabilities just by the nature of how to architect that and everything. So we'll see.
Sounds like it'd be pretty useful.
Yeah, it might be an interesting. I'd be interested to see if maybe they'll do something like that.
Because on Linux, that's exactly the use case.
Yeah, to keep people from writing kernel
The
mode.
programs get verified,
Mhm.
but it's not Turing complete.
Yeah.
And you have to be verified. Like it verifies that it'll complete, that you won't DOS. That
Mhm.
there's like a whole list of things.
Yeah.
And then it gets run in the virtual machine. So it's
Interesting. Yeah, I'm really interested in that. Yeah, if
I put in the live stream the link.
okay, cool. I'll take a look.
The interesting thing about it, the Linux gamers were very happy about it.
Okay.
If kernel land will be closed, anti-cheats will not be able to use kernel.
Yeah.
If anti-cheats will not be able to use the Windows kernel, all games can use Proton now on Windows, and
Yeah.
everything will be working. Because the only problem to simulate on Linux to play games is for kernel mode.
Okay.
And all the anti-cheats basically callbacks to the kernel. It's the biggest problem for gaming today on Linux. So yes.
Okay. Interesting. Yeah.
So when the crash happened,
Mhm.
the gaming community for Linux was very, very happy.
Gotcha. Yeah, that's there's actually a lot of overlap between the gaming community and this type of like binary exploitation in the kernel, because if you saw, I mentioned that termination driver that was used. So it was used by threat actors, but it's also very interesting to gamers, right? Because if you have some anti-cheat software, it's going to be implemented in the kernel, because that's going to be your strongest level of protection. Because if you have like a user, somebody that's running a as an administrator on their system, they're gaming, it's their systems, they're going to be administrators. So that if it's something that's not implemented in the kernel, they can just turn it off. And so that's why cheaters and gamers are really interested in that, to be able to see how they can subvert those controls and stuff like that. So there's a lot of interesting overlap between those communities for sure. So there's a lot of stuff on user mode here. I'm going to blitz through the different telemetry sources. So I mentioned callbacks before, and so the kernel has a lot of callbacks that essentially it allows EDR vendors or drivers to register with, and it's not just EDRs, but it's really anything that monitoring software and networking drivers and so forth. But there's kernel notification callbacks. So basically, you can register. Your driver can register with the kernel to say, "Hey, tell me anytime a new process is created," and it will do that. And then, like the EDR can say, "I'm going to inject my DLL into that process, and I'm going to overwrite some functions and stuff like that so that it can see malicious activity." So it does that for different events like process thread, images being loaded into a process, that type of thing. And then it can also like register callbacks for things like object notifications, like, hey, is somebody or some process getting a handle to another process, like LSAS or something really sensitive. And so you can see potentially malicious activity there. File system mini filters are what we all think of with antivirus. So file system mini filters are callbacks that are registered for file operations. So named pipes or the file system. So if you drop a file and it gets scrubbed immediately, that's because whenever you have this file write operation, there's a callback that's registered when that file is written, and that callback is going to scan it, and it's going to go out to CrowdStrike's. I'm going to pick on CrowdStrike to CrowdStrike's cloud, and it's going to like do a very quick cloud scan on it and so forth, and then it may take a second, and then it's immediately scrubbed. That's the file system mini filter in action. And then there's something called event tracing for Windows, which is probably where we're going to see most of the EDRs move towards. It's kernel mode tracing of events. There's user mode as well, but kernel mode tracing is really powerful because essentially you can track things instead of how EDRs have originally operated by like tracking events in user mode, like essentially seeing a new process, injecting into it, and then overriding functions to track them. It can just see the events in kernel mode, almost like servers, like if you're taking that user mode or the client server, web API and client analogy that I used before. It's like instead of having a client side control, like through JavaScript or something like that, you have a server side control or server side logging. And then it can be a little bit more transparent and you have to do less kind of hinky things in the kernel and in user mode to really implement it. And it's a pretty powerful source of data. And there's a bunch of other things like network filters and registry callbacks and stuff, but that's pretty much the extent of the main sources of telemetry in the kernel mode. So we're skipping over user mode, but kernel mode in general, you have three options to target things in kernel mode. And so your first option is a Windows kernel or native driver 0-day. That is really valuable. If you find one of those, you can probably sell it for about $1 million. No joke. To the right buyer. So if you go to one of those because they're so valuable for these types of purposes, if you want to sell it to nation state actor, I'm sure the sketchier the actor, the more money you can get, but the less you will be able to sleep at night, hopefully. But yeah, so it's kind of a career goal of mine to be able to find one of these and maybe retire. I don't know. But yeah, they're really powerful. Go ahead.
If you found one, what would you do with it?
If I found one, what would I do with it? I mean, I would. Oh man, that's a good question. I would not. I would not sell it to anybody scary. I probably wouldn't sell it. I don't think I would sell it. I would. There's if you know Steven Sims, you know Steven Sims from Sands. He's the offensive kind of operations researcher guy. He does like Sec 760 and Sec 660.
Yeah.
He has a series of he has a channel called Off by One Security, which does like all this kind of low level stuff. It's really awesome. And he's done a lot of work with, he has a couple videos and so forth on exploit sales and acquisitions. So there was stuff like CrowdFence and Zerodium, and ZDI was that was Trend Micros for a while, where yeah, exactly. Like if you found something really interesting, like Microsoft 0-day or something, you could go to one of these firms and you can essentially decide, okay, this person would sell to nation state actors that are NATO friendly. For instance, if you live in NATO, or you could go to somebody who's not NATO friendly, or you could sell it on the dark web or something. I would never ever do that kind of thing. I would find it interesting and probably try to negotiate with Microsoft to get a nice little pack. Yeah, something like that. And then I would feel a little bit better about myself that I didn't sell it to somebody who, well, what really makes me nervous, I get really nervous about pretty much anything. Like I found a bunch of driver vulnerabilities, and that's a really scary thing, because if you're talking to somebody who's like the driver vendor, for instance, and it's like a driver for some AV software or something like that, they might not care, or they might not even respond. And probably the latter. And then that's kind of a scary thing, because it's like, okay, well, there's this driver that's vulnerable that you can get kernel level code execution, but like nobody's responding to it. So at this point, I really hope that there are that the EDR vendors will start kind of coming together and kind of bulk up this LOL drivers project to be able to have better visibility into vulnerabilities that are being released and stuff that isn't being fixed. But for me, I'd want to sleep at night, but I'd also want to make a few bucks. So because it's a lot of work. Like to find a Windows kernel 0-day, it's a lot of work, because it's kind of, you can think about it like it's one piece of software that's been reversed and attacked for decades at this point. So you know, you're finding really deep vulnerabilities that are really difficult to find and really difficult to exploit too. So not only finding something interesting, but also weaponizing it to a meaningful exploit. Those are kind of two separate things, and both together are, that's why they're so expensive, essentially. So I would do good with it, but I would also have fun. Option number 2 is write a malicious driver and load it. So I already mentioned this before, writing a malicious driver, coding drivers is a really difficult thing, and it's a really dangerous thing, as we've established with CrowdStrike and so forth. So if you want to get into that, you'll find out that you can't just write a driver and compile it and then just dump it onto a brand new system. It's going to fail loading because it's not signed and it's not validly signed. So you essentially need to submit it to Microsoft and get an extended validation certificate, which is exactly what it sounds like. It's not just any old code signing certificate. It has extended validation where, you know, they do additional checks and so forth. And then also you have to get it cross-signed by Microsoft, which is a difficult process. And then they do all sorts of testing on it and try to see if there's any vulnerabilities and so forth.
Sorry, where do you get the EV cert from?
Well, you can get the EV cert from any,
It's cross-signed.
but you needed to be cross-signed. Yeah. So like you can get your own EV cert.
Yeah, I thought they got rid of EV certs. I didn't even think that was a thing anymore.
Yeah, we just got one for this purpose.
Yeah,
So,
I did EV certs like 15 years ago.
yeah.
That was a bit when they first came out.
Mhm.
They made the bar green. Made the whole bar green.
Oh, really?
Yeah,
Okay.
instead of the little lock, it would make the whole bar. And everyone's like, oh, people will trust us more because it's for kids.
Yeah.
Right?
Well, this is really the only thing I know of that. I mean, I don't do a lot of other cryptography stuff, but it's really the main thing that I think of when I think of an EV cert is this type of scenario, because they require it to be EV and then cross-signed. Go ahead.
Did they actually call you and see if you're real?
Yeah, I think so. So my boss did it. So we're in the process of doing this for like our trainings and for our red team engagements and stuff like that. Because if you can code your own, you know, then you have a lot more flexibility than trying to exploit something. You know, find some niche exploit somewhere. But anyways, yeah. Do they call you? I think they do call you. They do. I can't remember what they do.
They do a background check when they're trying to check if your company is registered.
Mhm.
They're trying to check where your physical location. They will call someone, will send them an email. We've had a lot of problems with them until we did our first sanity check, and it was only for a web problem, basically.
Mhm.
And then so the green bar, and it was $500 or something for
Yeah.
a whole year. And
Yeah.
it was a 2 months process to get the cert. So, and I think I did model back in the day. But
Okay. Yeah, it's intended to be a speed bump. Like it's intended to be something that's very difficult, so that you know a threat actor or whoever can't just do it quickly. So yeah, so that's option 2 is doing that, but most people don't want to do that, or it takes time, and you also have to have a valid location and valid information to be able to do that. And option number 3 is what I kind of focus on more recently, is loading a signed vulnerable driver. So something like in the LOL drivers. So this repository of known drivers, those are known at this point because they've been made public for the purpose of blocking them essentially. But a third-party driver, like I keep on pointing at the camera, like an audio video software or something that's implements its own driver, or something like an Nmap network driver or something like that. Finding a driver that has a vulnerability in it, because it's going to be less scrutinized than like the Microsoft kernel, and then loading it onto a system and then exploiting it to get kernel access. So basically, they've done the hard work of getting it signed or cross-signed by Microsoft, and so you can load it into the kernel, but it has some capability that you can exploit to then get access to the kernel memory, and then do your dirty deeds from there. And so the downside is, bring your own signed vulnerable driver. So you have to copy the driver over to the system. You have to create a service or modify a service to load a kernel driver, start the service, and then interact with it and exploit it. and then as kind of the payload or the purpose of that exploit, remove EDR telemetry if that's what you're trying to do, or escalate your privileges depending on the purpose. And then there's an optional restore of telemetry. So it's like you can remove the telemetry and then do your dirty deeds and then restore the telemetry so that it doesn't look like, you know, you're just being destructive. Go ahead.
I have a question.
Yeah.
If you have a signed driver and you inject the code through it,
Yeah.
basically the signature is not valid anymore because you changed the file.
Yeah, great question.
So what happened? So why Microsoft don't say, because it's essentially a different file already as soon as
Yeah.
you inject it.
Yeah. So that's a great question. So when you're exploiting a driver, you're not changing the file. So the signature is going to be checked when it's being loaded into the kernel land. But once it's loaded and running, there are other protections though. So I mentioned before HVCI, which essentially ensures that everything in every code that's executed in the kernel is signed. So what I find fascinating about this particular type and flavor of attacks is you're not actually trying to execute code. And that's when we get to the actual vulnerabilities. That's where I'm kind of going to stress things is I really try to avoid running code in the kernel as much as possible. What I'm really interested in is modifying kernel memory. Because if you can modify memory, then you can target the telemetry. So the telemetry isn't code, it's just like read-write portions of memory, essentially pages of memory, that it's like, oh, hey, here's the function address of a callback. And you can go and find that callback and say, okay, I'm going to clear that callback, and maybe copy the address of it in the kernel, and then use the vulnerability to remove that kernel callback. And you're not executing code in the kernel, but you are modifying memory of the kernel.
I have so many questions. What about the SLR?
Yeah.
Any other stuff, because memory will be randomized every
Yes,
time.
yeah.
And the driver will be loaded. Because essentially driver will be an hour executable.
Mhm.
And he will be taken as an executable that he's
Mhm.
running in kernel mode. So I understand corrupting some memory or exploiting some memory in the place to put your execution, but yes.
Yeah. So hopefully, I mean, I love these questions, by the way. But we might not get to some labs because of it. But if we do get to the labs, we'll cover that. And the exploit covers like an ASLR bypass, essentially. So the interesting thing with ASLR now, Microsoft is, to their credit, putting a lot of resources into remediating some of these issues or weaknesses or whatever you want to call. Not exactly vulnerabilities; they're more design flaws or architectural limitations. So you mentioned ASLR. So for those of you who aren't familiar with the acronym, that's Address Space Layout Randomization. And so it was first implemented in user mode. So whenever you have a new process, or rather, whenever you reboot, NTDLL or your Windows Server or your web server process or whatever, it's going to load at a random address rather than the same base address. And so everything's going to be computed as an offset from that base address. So like the code that's going to be run and the global variables and all that kind of stuff. And so what that does is it prevents an attacker from reliably predicting locations in memory. So jumping to a specific address in the code, or manipulating global variables or something like that. It prevents that because an attacker, on x86, it's a little bit easier because you could brute force in certain scenarios, but on x64 or 64-bit, you're gonna have a really rough day because you can't just brute force the entire base address space of a 64-bit process. That's just not feasible. So it's a protection in place to keep people from reliably predicting base addresses or known addresses. The kernel, they moved it to the kernel as well, which is KASLR, or kernel address space layout randomization. So on every reboot, the kernel is going to be at a different base address space. And the problem up till 24H2, so like one of the most recent major releases of Windows 11, basically normal user processes could just query the base address of any kernel module. So you can query and we do this in the exploit that I had for tonight. You basically run an API that goes to the kernel and says, hey, tell me all of the addresses of the loaded modules in the kernel. And it's like, okay, and it just tells you. So it's like really the only benefit it had was in low integrity processes. So if you had a browser process or something like that that's sandboxed, it limits the APIs that you can run to be able, so you can't do that kind of thing. What Microsoft has done in, I think it's 24H2, and yeah, I can't remember specifically what it was. I want to say it was 24H2, is you have to be in high integrity to do that. So basically you have to be running an administrator command prompt. And so you can still get all those base addresses of those modules, but it requires a little bit more privileges. However, the last line of this one is, to load a driver, you need to be local admin. So this is really beneficial if you're like in a pen test or red team engagement and you have local admin, then you can bring a vulnerable driver and you already have enough privileges to run in high integrity and then query those base addresses and run your exploit and so forth. So yeah, so there's a lot of things that are a lot of moving components and a lot of defenses that we have to overcome and that's what makes the exploit development process, as opposed to just finding vulnerabilities, so much more valuable, because finding a vulnerability is one thing, but overcoming all of the mitigations to be able to do something meaningful in the kernel is you know, a lot it's a much different story. So sorry, I went on a little bit of a tangent there, but hopefully that kind of addressed some of the things. Did you have any other mitigations or anything else you wanted to talk about? Okay, yeah. No problem.
Wait.
Yeah. So sorry, we're talking about like, 6 months of content in like, a very, very short amount of time. So, okay, so weaponizing vulnerabilities, kind of on the same train of thought here. So again, just what I was talking about, depends on the OS release and protections enabled. So VBS is for virtualization-based security. So basically there's a hypervisor that's run, there's the secure kernel and so forth. So it's a hardware protection that basically enforces certain protections, such as HVCI, which is going to require everything to be signed in the kernel. There's KCFG, which is kernel control flow guard, which is to try to mitigate things like use after freeze. They call it a forward edge. So a forward edge meaning it's protecting code that you're jumping to. So if you're overwriting like a function address in or something like that, and you're calling that, if KCFG or just CFG if you're in user mode is enabled, it's going to verify that you have a valid call target. So if you're just jumping to a random page of memory where you've allocated some malicious code, it's going to fail because it's looking, oh, you're going to call that. It's kind of being hooked, so to speak, and then it's being checked before it actually runs that code, and it's invalid. So that mitigation is going to kick in. So that's a really obnoxious mitigation that kind of wipes out certain classes of vulnerabilities like use after freeze and stuff. Maybe not wipes them out completely, but really makes them difficult to exploit. There's something called KCET. That's something that's, I'm totally blanking out on what that stands for, but that's what they call a backwards edge protection. So if you're familiar with ROP chains, it mitigates to some extent ROP chains and weaponizing those types of things, because it's like a backward edge checking your return addresses and so forth through like a shadow stack and so forth. So anyways, there's a bunch of different OS protections that really make our lives really difficult when we're trying to do things meaningful. But the good news is we're trying to only get read write in the kernel. So we don't care about, like I was saying before, we don't care about running code. So if it's like, hey, we can't redirect to our custom code, we don't really care about that. I just want to see if I can, write some null bytes or write an arbitrary D word or Q word of data into the kernel, and then or read it and / leak it and so forth. So there are a couple techniques to doing this. So one is called the kthread.previous mode. Again, you're going to hear me say this 4 or 5 times more tonight, but like it depends on the version. The most recent 24H2, I do know this one. 24H2 mitigates the previous mode overwrite. So basically, there's a 1 byte value in the kernel mode representation of your execution thread that tells the kernel whether or not this thread is a kernel thread or a user mode thread. And if you change it from a 1 to a 0, it's telling the kernel, hey, this thread is a kernel thread, so let it read or write to kernel memory. And so if we have a primitive, one of the first exploits I did was a write null where. So you could write a null byte anywhere in kernel mode. And so you can just find the previous mode structure for your current running thread, change it from a 1 to a 0 using this vulnerability that just wrote a random byte somewhere. And then that's all you really needed. And then you could just read and write to kernel memory. And the kernel would check this previous mode and see it's set to 0 now. And then it will let you read or write anywhere in memory because it thinks you're a kernel thread. So really, really powerful technique. It is starting to be monitored by EDRs. So if an EDR sees, hey, this process is a user mode process, and all of the threads that it's tracking in that process are user mode threads, and it starts seeing, oh, hey, now it's this particular thread is a kernel mode thread, it's going to say, hey, that's an exploit. Like that's some malicious activity, and it's going to trigger an alert. I know CrowdStrike does that. So that's been mitigated because really you don't have any instance where you would need to change from user mode to kernel mode mid-thread, so to speak. So they've mitigated that completely, where you'll bug check the system and crash it if it sees, hey, this was a user mode thread and now it's a kernel mode thread. So I know this is, I'm realizing now I'm moving like super fast through this and there's so much to talk about. So apologies if this is like, this is a lot of information, but it is what it is. So IO ring abuse is something that is available on the newest versions, Windows 11. And that's essentially a ring of buffer. It's a buffer ring that enables you to read and write to data. And you can modify where the ring is found and kind of make a shadow copy of it in user mode, and then use a vulnerability like an arbitrary increment or decrement to like find that kernel mode representation of the IO ring object, and then point it to your user mode buffer, and then give it kernel mode addresses to read and write to. And so you're subverting the protections essentially that way. So you're using these objects in kernel mode, and you're making minor modifications to say point to user mode objects instead of kernel mode objects, and then subverting protections to get access to read and write. Then there's stuff like memory corruption. So you mentioned ASLR. So if you're doing a heap corruption, and so the kernel mode heap in Windows is called a pool. So if you're doing like a pool overflow or something, you might be able to get to overflow an object, query the overflow to object, and then leak addresses from the kernel or leak data from the kernel, which will include stuff like, oh, hey, this is the process that created this pool allocation in the kernel. And then you see, oh, hey, here's an address in the kernel mode for the process object in the kernel, and then you can like traverse linked lists and stuff like that to leak all sorts of information and overcome ASLR that way. It's actually, in my opinion, ASLR is a lot easier to overcome in kernel mode than it is in user mode because of all these things. There's a lot of ways you can leak data from the kernel. It's not easy, but it's easier in certain instances. So yeah, and then there's things like unsafe mem copy, mem move. So if we do get to the demo today, the mem move, it's basically saying, hey, move data from here to here, and move arbitrary data to an arbitrary location. So if you hear me say write what where, that's what it is. You're writing what, you can control the what is being written, and where, you're controlling where it's being written, and so you're moving it around. And so yeah, that's just like kind of like a super basic and powerful memory corruption, because you're just completely controlling the data that's being moved. And if it's running in kernel, then you have full access to the kernel and you can modify anything. So yeah, I mentioned that's the arbitrary read write or write what where. There's arbitrary increments or decrements. So I mentioned that with IO ring abuse. What that basically means is there might be a vulnerability that allows you to give it an address, and then it increments or decrements that address. And so it changes a 0 to a 1, or it changes a 0 to an FF, by decrementing it. And so you can, find an interesting object in memory and then modify it to get that address to point to user mode or something, and then do all sorts of interesting things. I wish we could really dig into more of this to make it to let it make a little bit more sense. But again, this is like 6 months of information I'm trying to distill here a little bit. And then there's stuff like callback function overwrites. AV drivers do this a lot, where it's like, hey, modify the callback for this file operation, and you can say run this code, and you just give it an address, and it will allow you to run that code, and then you can do a lot of dirty stuff with that too. So yeah, again, load a driver with one of these types of vulnerabilities. There's more that we could use too, but these are my favorites and what I think are some of the more powerful ones. Exploit it to get read and write, and then enumerate and walk the different telemetry sources in the kernel, which takes a bit of work, but it's possible. And then just essentially remove or manipulate that memory. Okay, so let's do a quick demo. Well, let's try to make it quick. So it's 7:35. Are you guys okay if we see if, I don't know. I don't even know how long this is supposed to go. How long can I go?
Pause for questions.
Yeah. Let's do it.
And then...
Yeah, questions and then a quick break. Any questions? Go for it.
So you mentioned that when you're talking about the vulnerable drivers that you're copying onto the system whenever you get access, how often do you get blocked when you're doing that from EDR?
Yeah, great question. That's a really good question. It depends on the EDR.
Yeah.
Every EDR is going to be a little bit different.
Yeah.
And it also depends on the configuration of the EDR. So some EDRs are a little bit more aggressive, and you can configure them to be more aggressive. So for instance, I used to work at UPMC, and it's a very large hospital environment. So you'll see a lot of it's kind of harder to get a baseline of what's normal there. And you might have an EDR that's going to look for, hey, I've never seen this driver before, and so we're just going to block it because it's brand new and that's odd. Or it might be using other telemetry of activity that's on the system. So for instance, if it sees WinWord, and then it sees PowerShell, and then it sees a file write for a driver, it's going to be like, whoa, hopefully. And that's like other telemetry it's going to use to determine whether or not that's a bad behavior or not. But if you're it's running from an RDP process, and it's was recently a recently configured system, so it's likely an early install of some MRI machine or something like that, then it's likely a little bit more. So it depends on how good the EDR is in judgment, in making those judgment calls. Usually at this point though, while there may be some more alerting on the better EDRs for any type of driver loads, usually they're just looking for known vulnerable drivers. And that's really all they have, because we're essentially talking about exploiting 0 days here for a driver. But if you're using a known vulnerable driver, that's like either their threat intelligence, they're seeing, hey, this threat campaign is using this particular driver. There's a blog post that's released about XYZ driver that's being exploited. They can write a signature for that. I've seen with certain good EDRs, they'll actually block the interactions for the API calls. So like the driver that we're using here, this guy, I don't have the name of it. It's the dbutil23.sys. It was a Dell driver, so it was released to millions of systems in 2021. And so it's very common out there. And so it's really hard for like a CrowdStrike or a SentinelOne to be able to say, we're just going to block this driver from loading, because you could have a system, because it was so widely deployed, that's legitimate and it has it on it. So it can't just block it writ large. But what it will do is it will find the specific code that's going to exploit the vulnerability and block that code. And that's a pretty impressive functionality. But that's because this is such a well-known driver that's used for this purpose that it can do that kind of thing. So if you have an unknown vulnerable driver, you're going to have a lot easier of a time doing this. But again, that's a caveat of there's a lot of other things that the other telemetry sources that the EDR is going to use for that kind of thing. So probably more than you wanted to know, but a really good question. Yeah.
Couple questions.
Yeah.
Will this PowerPoint be available after?
Yeah, we could make this. Yeah, I can make the slides available.
And
Yeah.
is this covered in White Knight Labs? So,
Yeah. So we have the offense. So this is not intended to be a marketing statement, but I added the Bring Your Own Vulnerable Driver content to our offensive development course. So what we do is we use a known vulnerable driver to implement a lot of these techniques, and the POC that I was going to show in the lab is the one that we use in the course. It's just the basic one. We don't show all of them, but what we do is we go through loading vulnerable drivers. We talk about enumerating certain telemetry sources in the kernel, and so we use it like in WinDebug. We just look at memory and see what it looks like in the memory, and then we do it in the code as well. But it's kind of under active development because it takes a while to get it all in there. So, do you have other questions? Oh, okay, I got you. Anything else? You guys want to take a quick break? Or do you want to keep powering through?
Keep going.
All right. I like it. All right, cool. So,
Why are you doing it in 10?
what's that?
The demo. Why is it in 10?
Why is
Been
See Windows /temp/d-utils.
Oh, yeah. This doesn't really matter a whole lot. So you'll find that if you're familiar with drivers, you'll usually find the native drivers are in C, Windows System 32 drivers. That's the typical location, aside from a few other ones. It really doesn't matter where they are, but this is just actually what I just copied and pasted this from LOL drivers because it gives you the code to do that. So I actually put it in just my downloads folder. It doesn't really matter, but there's no particular rhyme or reason to that. So yeah.
What language do you use for writing that policy?
Yeah, a lot of times it's C, C++. I usually do C. The POC we'll use tonight it's C. Ooh, there's pepperoni. I didn't see there's pepperoni.
This came. Go get
Oh,
some.
dude, there's like 30 pizzas over there, man.
Yeah, they just brought 3 pizzas.
Man, maybe we should take a break now.
Everyone's like, wait, there's pepperoni.
Yeah, exactly. Everybody's getting up now.
I changed the pepperoni.
I'll get some a little bit later. Thanks. So I see. I get greasy and then I need to wash my hands, and so I'll just wait.
That's why you gotta pre-dab it.
Yeah, pre-dab it. See, I'm too. I don't want to touch my computer after. Like, I need to wash my hands, or I'm gonna have like a, twitch. Somebody asked a question. Oh, you were asking what? So you can use pretty much anything that interacts with anything you can run a Windows API with. So
.NET will be working as well.
yeah, it's more difficult. I've tried to implement certain things in C#, and it's difficult. And I was trying to think of that today because I did it like 6 months ago because I was more comfortable with C# when I started than with C. Now I'm a lot more comfortable with C.
Back in the day, I tried to use Python to make C.
Yeah.
C code basically too, but it's hard.
Yeah.
You need to write a lot of structs
Mhm.
to work correctly, and it's a pain.
Yeah. So a lot of people will use stuff like CPython or C types, that kind of thing, which will allow you access to C types from Python, and Python's written in C, so it's kind of, or it's, the original code is written in C for Python, so it kind of has that undergirding foundation for doing that kind of thing. But it's not, I wouldn't say it's super great. Like you said, like you have to define types, and there's all sorts of interesting things that you'll have to dive into with like the structs and all these definitions and so forth. So I think that C and C++ are probably the best to really get into it. But that being said, there's more signatures for those, excuse me, for those types of things. So if you want to write it in Go or something like that, or Rust, it's probably a worthwhile endeavor
There's
to.
another interesting technique what you can do. It's a little bit pain to write. but
Yeah.
Basically, what you can do, you can use leverage PowerShell.
Yeah. Mm-hmm.
Into PowerShell, load into memory .NET modules. So basically C#.
Mhm.
And how it works, PowerShell called C#. C# is running into memory.
Yep.
And the C# program is basically loaded to a memory without writing to a drive. So it makes sense.
Yeah.
You
Yeah.
can try to do with the whole exploitation, but it's a lot of code. It's tricky to load correctly, but
Yeah.
it will work. And it's very, very hard to detect because not back in the day, not all the AVs was doing good memory
Mhm.
detection. I don't know what happens today in the API world. I'm not
Yeah.
working malware for the last 3 years, so
Yeah.
for me it's hard to.
Yeah. So, John, right? So John was asking about AMSI. So AMSI will start to see that because, like within PowerShell, a lot of times you're essentially invoking .NET code, like you were talking about. So a lot of, if you'll see, like the Ruben Bunin, who's from IBM X-Force, he's like their head of research. He has a really awesome like intro to kernel exploitation series, and he does it all in PowerShell. And so he like adds the types, and then he does platform invoke, which is a way to invoke the Windows APIs from PowerShell, which is essentially what you were describing there. And so like it's all possible. It's just there are certain things that are a lot more difficult, and I've run into roadblocks from like, wow, this one thing is really difficult to do from C#, and I have certain things like there are certain things that are more scrutinized by EDRs from one type of like, so calling out to GitHub might be super benign from, or super benign, but reasonably benign from a managed assembly in like a .NET assembly. But then when you have unmanaged code from like C++ or C doing the same thing, it might be flagged. So it's a little bit odd. So I have certain things that will be like, maybe it's like a cradle of a managed code from .NET, and then it calls an unmanaged DLL, and then like runs that natively. And so that seems to work pretty well. It just depends on which EDR and what they're kind of scrutinizing more. But if you have things that are less common, like C and C++ is kind of your standard malware development.
I never like to develop in C or C++.
Yeah.
I hate the languages.
Yeah.
It's my own problem.
I feel you.
The second problem is because the binary signature was a big deal,
Mhm.
and you want to bypass the binary signature, so you always will go to interpreted languages.
Yeah.
And you will try. So yes, the road is much difficult
Mhm.
to run or execute a simple thing, but in the same way, the benefit is bigger because the evasion is much easier.
Yeah. And there's been a lot more effort to try to target like .NET and .NET plus PowerShell and all that kind of stuff, and it's getting a lot better, a lot more difficult but it's still a really great way to go if you're trying to scoot around some detections and so forth. So yeah, great questions, great comments. Anything else before we go into? Okay, cool. Well, let's power through a bit. Stop me whenever you want. If you guys are like, I need to go, or I just want to eat pizza now, like we can stop whenever, because I know at this point we're getting pretty late.
Are you doing the workshop now?
Yeah. Is that okay?
Yeah.
Okay.
No,
I heard power through, so I'm powering through.
I
So.
was just trying to catch up and get some stuff installed.
Okay.
And
Okay.
Lab and
I was gonna
Virtual.
do that. I was gonna do that.
Okay,
So
cool, yeah,
you'll
get
have
together.
time. Yeah.
I learned how to RDP into a Windows box today. It was pretty sweet. I have not been on a Windows box in over like 10, 15 years. This is legit.
I
Like,
will hold him only for this.
I didn't even know.
Years.
Did you know? Like, you get like a private key and you like
Yeah,
decrypt.
You
the
decrypt it.
admin
Yeah. So we're gonna do this. So we're doing this right now.
That existed. Like,
Yeah.
this is sweet.
I stopped using Windows for the last 5 years, so
That's what I'm saying. This is a learning experience.
Yeah.
as I stopped developing malware, I stopped using Windows.
Yeah, exactly. Because why else would you use Windows, right? So if you're following along at all, it's pretty simple what John was talking about. It just go to Actions, Security, get Windows password, and then you upload the key that you configured for this instance. I'm going to do that so you guys don't see. me upload my private key.
Can people see in the video, John? Because it's kind of reflective.
Yeah, no, I mean it's as good as it's gonna get.
This is the only machine I use this key for. So if anybody sees it, I really don't care. Because I'm going to just destroy it in a second. Same thing with the administrator password. So you're going to see my administrator password, and I just don't care right now because after
What's your IP?
60, yeah, I'm gonna copy that too. You're going to see it all, but literally, it's just this totally vulnerable server 22. Yeah. So. Yeah, exactly.
It's like it's on the live stream too. So.
Let the mining begin.
Yeah, exactly. Yeah. All right, cool. So here's my IP for all of those who are wondering. Oops, I didn't mean to close that. I meant to edit that. Okay. All right, administrator. So I'm just RDPing in.
So you put it in your history too.
Uh-huh. Yep. All right, get on off your high horse. Okay, it's just a lab, all right?
I've been in your shoes, man. People give me so much crap for stuff like that.
Yeah, there's always somebody who's like, you're showing your password. I'm like, dude, this is for the training, okay? Like, I'm not using this to store anything sensitive, and it's going to be destroyed in 2 seconds. Yeah, exactly. Yeah. Okay, cool. So that doesn't really matter here. So what we're going to do, this is just a totally vanilla Windows Server 2019. So we're going to install Edge because we only have Internet Explorer, of course. So we're going to install Edge real quick. Sorry, this is going to be a little bit of setup. I ideally wanted to get an AMI and just like kind of have it all turnkey for everybody, but who wanted to do it, but it's just, I didn't have the time. So apologies. Oh, that's not it. It's our browser.
I
Oh,
gotta
my
say,
goodness.
I love the experience hasn't changed in a decade.
Almost 5 years old.
I mean, maybe 15 years.
Yeah, well, this part is 15 years old.
Yeah.
All right.
Even
Save
the
it.
installers, like all these next finishes, I forgot about this stuff. I
Yeah.
seriously forgot about all of this. It's,
Flashbacks.
yeah, no, seriously.
Are you okay?
It's been a long time.
So what do you use on the day-to-day?
Mac and Linux.
Okay.
Yeah. Well, yeah, these are Mac. That's mostly what I use.
I love that. I love this. What is it, Space Black or Space Gray or whatever it is?
Yeah, Space Gray, yeah.
I always. I think when I got this one, they didn't offer it, or maybe they just didn't have it though. Oh my god! But this is just. Is that an M3?
Yeah.
Okay, this is an M1, a little older. Yeah.
Same.
I love the M1 or the I.
Oh, the ARM? Yeah.
Yeah, I think they're great.
Early on, the M1s were rough.
Yeah.
Because nothing supported ARM yet.
Yeah.
But by the time we got to M2 and M3, it was
Mhm.
the ecosystem covered.
Yeah.
How do you do exploit development on the Mac if you cannot compile it x86?
RDP. Yeah. No, I have a Windows 11 system at home that I do. So I have VMware on my Windows 11 system. It's Intel, and then I have 2 Windows 10 systems or a Windows 11 system. So Windows 10 for remote debugging, and then Windows 10 victim and a Windows 11 victim. So, and the reason for that is so we're going to do local kernel debugging here, and what that means is we're going to debug on the same system. We're going to debug on the same system that we're debugging, if that makes sense. So we're actually looking at the kernel on this system. Remote debugging is where you debug on a different system. So it's essentially a safe system. So if you're trying to do something weird in memory, or you're trying to look at the kernel, or you're crashing or something, you can analyze the memory after the crash, before it reboots. And so you can see, you can modify data, you can read, write, you can look at cal stacks and all that kind of stuff. So we don't really need that today because we're not, yeah, ideally. I mean, somebody's probably going to crash. If you have 5 people that are doing this, I mean, I crashed this morning when I was doing this because I did something silly, but I'll probably do it again. But
When you say the local, you're talking about the virtual machine.
correct. Yeah. Sorry. Yes. Thank you. Yeah. So I'm not talking about my Mac. Yeah. So local meaning local to the system we're remoted into. So yes. Thank you. All right. Cool. So now we can just download WindowBug. Well, you can get it from the store. I actually like the one from the store a little bit better because it's prettier. I had the. I'm just going to. I would recommend if you're following along on this Windows 7, or what's oh my goodness, this Windows SDK/archive. This is the one that I would recommend for this one, just because the default install of Windows 2019 doesn't have the store or anything like that on it. But if you're like following along with, Windows 10 system or whatever, you can do that. So install SDK just right here. Open it up, and we're just going to do a minimal install for time and space's sake. And we do not want to send anonymous data to the Windows. Do not send your malware, or well, if you don't want it to be burned, don't send your malware or your exploit data to Microsoft or VirusTotal or anything. Yeah. Don't upload your viruses. I mean, unless, yeah. Antiscan.me is pretty good. It doesn't upload to anything. At least last time I used it. Oh man, dang.
What features are you selecting?
Yeah, so the only thing that we need, sorry, I know it's a little bit small here, but the only thing we need is debugging tools for Windows. That's going to install what we need. And it's a half a gig, so it's a lot smaller than kind of the entire suite. So
This page right here. Can you tell me that does not look like a phishing page?
it looks like a phishing page.
This is Microsoft.
That looks very much like a phishing page.
That's actually apps.microsoft.com.
Sounds like
I'm trying.
Okay, so this is all installed there. And the next thing that we need to do is actually install Visual Studio. Really, all we want is the cl.exe, so the command line compiler. And I'm sure there's like a leaner way to do this. I'm 100% positive, actually. But just because I have some tooling and so forth that already uses this, I just wanted to keep it consistent. So, all right. So if you've installed Visual Studio before, it's beefy as all get out. So that's why we had to kick it up from 30 to 50 gigs. Excuse me.
Just out of curiosity, I've never used Visual Studio.
Uh-huh.
So what is the difference between this and what they used for VS Code?
So Visual Studio, like you can get all of the Visual Studio code is really, in my opinion, it's really good for stuff like Python or PowerShell, like those types of things, like interpreted languages, like we were talking about before. If I'm going to do something with like C, C#, C++, those types of things, or do something kind of very Microsoft heavy, like you see like Azure development here and ASP.NET web development and so forth, I'd use Visual Studio just because it's going to have like all the packages and all that kind of stuff that's kind of well taken care of. You can also get Visual Studio. Visual Studio Code's also a lot leaner, and I don't use Visual Studio Code all that much. If I'm not using Visual Studio, I'm usually using VI or something like that. So, or maybe even like Sublime or something. But like I wouldn't do Python development in here, even though it's an option. So all we need to do is this desktop development with C++, and it's going to natively support C as well. You can see total space required of 11 gigs, so that's a lot. But that's okay. We can just install it in the background. It's going to take, well, we're still at 0, so it's going to take a little while. But what we're going to do while we're waiting is we're going to look at the kernel debugger. So whenever you're doing anything in the kernel, whether you're looking at like EDR telemetry or you're looking at like exploitation or anything, it's just so much, I find it so much easier to learn by looking at the memory, examining the different structures and so forth that we're going to target and we're going to attack. So what we're going to do as the first lab is we're not going to deal with any drivers or any vulnerabilities per se. We're just going to mimic the behavior that we're trying to emulate or we're trying to achieve in WinDebug. So if you remember what I said before about like reading and writing to data, that's essentially what you can do with the debugger, right? You can just say, hey, change this 1 to a 0, or pause execution here and tell me what arguments are being passed to this function or anything like that. So we can read memory in real time and we can manipulate it. And so we're going to do that with WinDebug, and then maybe if we have time, we'll actually go through the kernel exploit and talk about that a little bit more. So you should be able just to do WinDebug. And it's going to give you a couple different options. We're going to want the x86 version. And then I always pin it to the taskbar when I install it, just because I use it all the time. This is going to be a little scary if you've never used WinDebug or any type of debugger before, just because it's a lot of like commands and things, but it's just like Linux command line or anything else. Like once you use it a lot, then you get a lot more comfortable with it. And this is small, I'll make it a lot bigger. So you can do Control K. And if you do Control K, that means that we want to switch to a kernel debugger. And if you see up here, you'll see net, USB, blah, blah, blah. We actually want the local, because if you do net, that means that you're going to act as the debugging client, so to speak, and you're going to connect to something that's exposed a kernel debug port. So we're not going to do that because you need 2 systems for that. It's more powerful, but it's a pain. And so we're going to go to the local tab and just do kernel debugging of the local machine. And so you can hit OK, and we're going to get an error. Does anybody have any idea what that error could mean? Or why we're getting an error? Based on maybe some things we've talked about tonight. So really great guess. Just the way that we're running on the server, we're logged in with an administrative user, and UAC is essentially disabled. So anything that we run is essentially going to be run in high integrity. So we have the privileges to do this, kind of, from that perspective, from a token perspective. The problem is, it does say local kernel debugging requires administrative privileges. The problem is driver signature enforcement. So if you remember, I mentioned before how Microsoft zealously protects their kernel. And so they don't even want you kernel debugging unless you're in a specific mode. So we actually have to tell it we're going to be in debug mode to enable this to happen. And so debug mode is going to disable the signature requirements, so we can load a like a test server or a test driver or something like that. So we're going to enable test signing mode so that we can either debug like we're doing, or we can load like an arbitrary test driver or something like that. But they require you to set the setting and then reboot it. So it's not something that an attacker can easily do without being a little bit more destructive and noisy. So all we have to do there is, well, we're in the middle of course, we're in the middle of downloading that. I should have thought of that, but you can just do Control R, CMD, and then BCD edit -debug. Actually, let me make this bigger so we can all see it. Properties, font, go to 24. How's that? Big enough? I'm going to make it a little bit bigger than that because we're not going to be doing a ton of commands, so might as well make it big.
Isn't the EDR going to comply with debug?
Depends on the EDR. Not always, actually. So I've done a lot of testing with CrowdStrike, and it doesn't seem to really care. I mean, we're using a Microsoft, like they offer it on their store. So it's actually, there are certain researchers and red teamers and stuff like that that will use WinDebug to write payloads into memory and then redirect execution to it, just all within the debugger, which is a pretty fun activity. Because you have like full memory access and you're using a living off the land tool with Microsoft. So yeah, CrowdStrike, or I'm sure some vendors would, well, let me reframe that. If you have debug mode on, like we just turned on, and you reboot it, and then you try to load a odd driver, like a test signing, like if you're just like writing a malicious driver and then loading it, it will see that, and it will see, oh, there was a driver load event, and then it will look at the load, and it'll see, oh, it doesn't have a valid signed driver. Why is that on the system, and so forth, and then it will trigger an alert. So for instance, early on when I was doing this type of research, I had I mentioned there was a vulnerability, like the first vulnerability I was working with and weaponized was a write null where. And so you just write a null byte or a Q word or D word of null bytes to the kernel. And so one of those things I did was find the bytes in memory that determine whether or not you're in debug mode in the kernel, and then just change that from like a 6 to a 0. So 0 meaning like debug mode. It's been a while since I did it. And then loading my own driver. And so like making a malicious driver and then loading it. That got flagged not when I turned debug mode on, but when I loaded the driver. And so it saw there was this weird driver, and then it probably saw that I was doing some weird things with that driver, and then it sent an alert to CrowdStrike for that. So it's kind of a roll of the dice. Like really anything could really make the EDR scream, but it definitely requires a lot of, monkeying around, so to speak. So yeah, good question. Good question.
While you're waiting for that to download, and did you know that if you use a T3 large, that you would get like substantially faster internet?
Really?
Yes.
Man, the more you know.
Yeah.
I have to learn to cloud sometime. It's also cheaper. Yeah. See, I'm using my work account for this, so I don't really care.
It's cheaper, faster, and has better internet.
That is great to know. So you're all done then?
No, I actually never got Windebug to install. It got too complicated.
Yeah, I feel that.
I feel you on the making an AMI. Have you ever used like Packer?
I have not. I've used tools that have used Ansible and Packer and stuff. We, for our trainings, we have AMIs, and I'll eventually get more experience with it. We essentially have a bunch of AMIs that have like EDRs installed and stuff like that, like Elastic and CrowdStrike and all that kind of stuff. I don't know. I don't do that. My boss does that. So
if you're in AWS, that's the easiest route.
Probably what it is. Yeah.
EC2 image builder. Packers like that.
Think about Windows, the last update. I know. Not the last update, but one of the
last
updates they added the command line tool. You can do like apt-get install.
Yeah.
But for Windows.
Oh, nice.
So there is all the packages that you can install automatically. So if you script it.
Yeah, I was trying to install WinDebug that way, and it wasn't working.
See, I was
like WinCMD or something like WinGet.
WinGet, yeah.
Yeah.
So if you Google how to install WinDebug, it's going to be WinGet.
And then I opened PowerShell, and it still didn't work. And then I was like, "Where's this new terminal I heard about?" And
yes.
I had to download a whole other thing, and I'm like, "I give up."
See, that's why I had very specific instructions just to get that installer, and I was trying to save everybody from that pain and suffering.
You should do shortened URLs.
Ooh, yeah.
I could type it in.
Ooh. And pro tips flowing in.
There you go, boom.
All right, let's do it. We're starting it. Yeah, I should have thought of that.
I got.
Yeah, I'm gonna get the. You get all the merciless heckling after this. So, okay, yeah. So that
goes throughout. That happens throughout.
The throughout, yes. There's no sparing throughout. Okay, so we're at this spot, right? BCD edit / debug on. We'll download the driver later on, but now if we do glow, what was it, lab, token swap. So this is what we're going to do for the first lab, and this is what a lot of kernel exploits will do, some iteration of this. So in Windows, a token is what manages your privileges for a specific process. So if you have like a system process, it's going to have a token with information on it. Or tracked in the kernel. And so it's all managed and tracked in the kernel. And it's basically an address to an object that lists all of your permissions. So what most kind of vanilla, normal kernel exploits do, not like EDR attack type stuff, but just normal, hey, we found a kernel vulnerability. Most will try to inject a shellcode stub, a very short one, maybe 50, 60 bytes, something like that. And what that does is it loads the kernel process structure for the current process and then it reads the linked list of processes until it finds PID4. Does anybody know what PID4 is in Windows offhand? PID4 is like a known number of process ID. That's the system process. So it's like the mother process, so to speak. And so it's always going to be run as system. It's going to have the highest privileges, and it's
like PID 0 in Linux.
exactly, yeah. It's just 4 in Windows, and the modules and the DLLs that are loaded in PID4 are actually drivers. So it's essentially the kernel process. So instead of DLLs, you'll have .sys files. It's the same file type, but it's just they're drivers instead. So a lot of times, just because it's a known PID, it's always going to be 4. The shell code or whatever the exploit primitive is going to search through the linked list of these processes in the kernel until it finds PID4. When it finds PID4, it's going to reference the offset for the token, which is in that structure. And then it's going to read that keyword, which is the location of the token information. And then it's just going to copy that keyword. Does everybody know what I mean by a keyword? So a keyword is 8 bytes. So if I say keyword, it's like a location, a pointer, basically, a pointer in the kernel. It's going to read that pointer, copy it, and then because we have read and write with this shellcode in the kernel, just copy paste that pointer to our current process, and so that it's elevating our process. So anytime our new process is going to do something, the operating system is going to check the token to see if it has the permissions to do whatever we're doing, and it will see that we're the same token as the kernel, and it's going to let us do anything the kernel can do. And so all we're really going to do is copy that, and we're going to do a whoami/all. When we do a whoami, it's going to query who we are, what our token information, and then the kernel is going to tell us what the token information is, but we're going to be running with the copied system token. So a lot of times that's run through a shellcode stub, like, hey, we've injected code into the kernel and then redirected execution to it. That's kind of the classic. But like I said, a couple times, or alluded to a couple times, there are a lot of roadblocks to executing shellcode in the kernel, especially because it's not going to be signed, it's not going to be part of like a signed driver or anything like that. So a lot of times what I'm looking to do is just find that direct memory access in the kernel, and then you just read that token through direct memory access through like, impersonating a kernel thread or something like that, reading that memory, and then writing that memory to the current process. Essentially, they call that a data-only attack. So that's becoming a lot more popular in the binary exploit development space. Data-only attacks mean you're not executing code to accomplish your goals. You're just modifying data. You're just read-writing. And so it's kind of like taking a step back from, do we actually need to execute code to accomplish our goals, or can we just modify something in memory? And because so many exploit mitigation controls are focused on preventing code from being executed, that read-write tends to be something that gets a little bit overlooked. And it's really hard to mitigate. Go ahead.
But it's the same idea, basically, like a buffer overflow.
Yeah.
When I'm doing buffer overflow, I'm not executing because I'm just writing it, hoping that someone else
Mhm.
will execute me.
So with a vanilla buffer overflow, typically what you're doing, yes, you're overwriting past the bounds of a buffer, which is typically on the stack, and then you're overwriting data to write beyond the bounds in the stack to eventually overwrite a return address. And then typically, once you hit that return address, it's going to go to somewhere else where you want it to go. A lot of times, kind of the classic example is like a jump ESP type of scenario where you write a shellcode on the stack and then you jump to the stack pointer. And there are other mitigations in place that make that really difficult, but still you're writing shellcode to the stack and you're redirecting it to it. And so that's still kind of in kernel mode, and that's going to be prevented by a wide range of mitigations.
No,
So
I mean, the idea is that
Mhm.
you're still writing you're trying to find a memory address where you can write it.
Yeah.
To the memory address. And
Yes.
the same thing is here.
Mhm.
You're basically trying to find an address where you can write it. So
Yeah.
This
Yes.
buffer overflow, only the right address.
Mhm.
I don't understand still here how you do the execution because you just wrote to the address. Your code is not.
Yeah. So this would not be through a buffer overflow. If you have certain mitigations disabled and so forth, this would be through something like, say, you can control the arguments to a mem copy. So you can say, copy source to destination, and you can control the destination and the source, or you can maybe predict. You can predict and modify the source location. Maybe it's like a global variable or something that you can modify, and so then you could like move to the destination. So this is not for every single vulnerability, but like the shellcode stub in your buffer overflow example, if you could redirect to that stub, it's going to do this in the shellcode. But if we are having difficulty for whatever reason, the protections like in user mode it's called dep, but like no execute, non-executable stacks and so forth. If we can find a way to just modify the memory, like impersonate a kernel thread, like we talked about before, then you can just read. You just get the address and you just read it from user mode, and it will provide it to you.
I don't understand who makes the execution.
So,
Because it's linked
yeah.
to memory.
Yeah.
So in my understanding, if I want something to be executed, someone need to apply it, some function or something in the kernel needs to read it and run it.
Yeah. So, and sorry, this is I've glossed over a lot of the details that kind of clarify some of this. So in this example, like impersonating a kernel thread, you have a user mode like process, and you're running with a thread, and through your exploit, you modify memory in the kernel. So let's say you can change a 1 to a 0 through your kernel exploit, and you find your thread in the kernel, and you change the 1 to a 0, which would indicate whether 1 being user mode, 0 being kernel mode. And so when you try to send an API call from user mode to read or write to a certain data, the kernel is going to do a security check and say, is this a user mode thread or a kernel mode thread? And it will see, oh, you're a kernel mode thread. And then it will actually let you read and write to kernel memory from user mode. Exactly. Yeah. So sorry, we kind of glossed over that. And that's just one technique. There are other techniques too. So I mentioned that IO ring buffer. And IO ring buffer is like essentially you can queue a buffer of read and write operations, and then you can queue that up with, and it's going to check and see if you're a user mode process, you can only write to user mode buffers. But what you could do is it's like copied into the kernel after it's checked and it's like past the check. Then you can modify the pointer to that queue of buffers to point to user mode, and then modify that user mode buffer to point to kernel addresses. And so you're just like doing all this kind of deception essentially in kernel mode and user mode to cause it to point to things that it should be pointing to. And so that's essentially where exploitation has kind of moved, at least the type of stuff that I've found to be useful. Because trying to actually execute code like through a buffer overflow, there's just so many mitigations to overcome, and when you can just like flip a 1 to a 0 and stuff. So yeah. Yeah, so it'd be from user, yeah. Or if you're doing from that queue, you kind of submit that queue to be done, and then there will be, it will transition to kernel mode. It will check, and because you've already passed the checks, the checks have already been done. It trusts that, and then we'll just write to it. So unfortunately, yeah, those are like, maybe we could do a future one where we actually dive into one of those in a little bit more detail. But so that's kind of the general idea for now. So we should have our thing back up. Great questions. Any other questions while we're, aside from what my password is?
Does Microsoft provide symbols for kernel mode APIs?
Yes, great question. Many, there are documented and undocumented APIs and functions and so forth. So you'll see, like in the course that we teach, we go through There's like global lists and so forth that do have symbols that are published, like callback lists of the callbacks and so forth. And those are there are some of those that are publicly listed. However, if you are, say, you don't have symbols or anything, and you're running from an exploit process, and you're trying to target some of those lists, what you can do is do things like, so for instance, it might be published in the symbol, but you don't have access to the symbol. I try to hard code things if possible, just because it's easier. But you can actually do memory scanning. So there might be a function that's exported, and then at some point in the function, it jumps to another location, to an undocumented function, and then that undocumented function references the array that you're looking for in the memory. And so you can kind of walk that list, like find that jump, find the offset, read the memory of that code, and then until it gets to the offset for that array, and then read that array. It's an ordeal, but it's can be pretty fruitful when you're looking for, like, there's certain, you can kind of use you can use documented APIs and documented symbols to look for things that are undocumented at times. And that's usually a really good technique, is like find the the APIs or the functions that are exported, and then look for something that's kind of cross-referenced or referenced in one of those functions, and then read those offsets and so forth. So yeah, it's a lot of work. A lot of this is like really annoying stuff at like a very low level binary level, but then like when you get it working, you're like, oh, that's awesome, but it's like, oh, this is so much work. So anyways, okay, so fire up WinDbg, and we're gonna do Control K and go to local and hit OK. So I'm gonna make this a lot bigger because it's ugly and small. See, I'm having to like go super close even here. View, font, maybe 20. Is that big enough? Can you guys see that okay? Make that a little bit bigger if needed.
You're using WinDbg because it's coming with Windows, or?
Yeah, I like it because, yeah, it's a Microsoft product. It's pretty full featured. It can be a little annoying at times. I don't think it's like the cleanest or the easiest like commands and stuff like that, but it's kind of like Linux. It might appear to be really weird and obnoxious and esoteric at first, but then like you do it and you're like, oh, okay, I guess it's starting to kind of make sense. So I'll explain the commands as I run them so that they kind of make sense. A lot of times it's like, there's a letter that stands for a word, and then I'll kind of explain those as we go. But yeah, I don't even know if there are other really comparable kernel debuggers. There's plenty in user mode, like x64 debug and things like that. I even like using WinDbg for, I favor WinDbg at this point over x64 debug just because. Yeah. Oh, cool. Okay.
Back in the day, you can use ODBG.
Yeah.
So ODBG could do kernel stuff as well, but ODBG supported a lot of plugins.
Mm-hmm.
Import a plugin.
Yeah. Interesting. I loved Ollie. Ollie was great. Yeah, x64 debug just doesn't have the same magic to it. Doesn't have the same flair. But Ollie and Immunity, those were fun. Immunity had cool colors to it. I liked the colors for Immunity. Okay, so what we'll see here is, you mentioned ASLR, so this will tell upon loading and attaching to the kernel what the base address is. So it's saying the kernel base is there. So every time we reboot, it's going to be at a slightly different base address. And we can list. So first thing that we can do is do .reload/f. And what that's going to do is it's going to reload the symbols. So Nate mentioned the symbol files. And so we essentially point, this happens by default. It will point to Microsoft Symbol Server, and then it will walk all of the modules that are loaded, like all the drivers and stuff. And then it will reach out for each of the drivers to Microsoft Symbol Server, and we'll try to grab those so that based on the version of the file and so forth. And so it takes a little while because it's making all these web requests out. And if you are not connected to the internet, like if you're trying to debug EDR or something and you don't want it reaching out back to the EDR, this is going to take like 5 minutes to do because it's going to keep on trying and failing. So
Something that's cached.
some of them are cached, and like if we rebooted it, I think it will show where they're downloaded once it's finished. It's almost done. But you'll see the file location of where they're downloaded to.
I was just wondering if you could like download and cache it, copy it over,
Yeah.
cut the internet.
Sure. Yeah. You could totally do that. Like if you wanted to download all the symbols and then install EDR and then cut it off, that would totally be fine. Just and then you wouldn't be updating any of your libraries, so you wouldn't need any new symbols, likely.
Yeah, there's like a file open symbols thing where you can just ignore them.
Yeah, you can just like copy and paste them over too if you just want to go. There's some really great repos recently that have been released that will allow you to like they are databases of the file, like offline versions of Microsoft symbols files, like kind of almost like mirrors of them that are super useful for vulnerability research. I use them in my EDR tools because I was mentioning offsets. A lot of times, all of the EDR telemetry, they're going to be like lists or something that have a specific offset. And so it's going to change for every version. And so if you're just writing to an arbitrary offset, you're going to crash your system every time. So you have to be very careful about the offsets. Even when we do tokens here, we're looking for the tokens to swap, but that offset can change whether you're on a server, whether you're on a workstation, whether you're on version 2022 of the server, whether it's November 2022 versus December 2022, the offset could change for the token. And if you're using a payload for the wrong version, it's going to reference the wrong offset and it's going to grab the wrong data and you're going to crash. So this is taking way too long. So I don't know why it's.
Did you know that if you use a T3 large, you
can It's done. All right, it's done. Okay, right when you were talking. So you can see there's a bunch that is not found. As you can imagine, you see. Does anybody know what this is? WD filter. Any guess what that could be? Based on what we're talking about tonight. Windows Defender filter. So that's the kernel mode driver for Windows Defender. So whether it's enabled or not, it's going to still be loaded. Even if you have like CrowdStrike or something else on here. I know I always use CrowdStrike for some reason, but I like picking on them because they're really cocky. But yeah, so even if you have like CrowdStrike on here, you'll see csagent.sys, but you'll also see WD filter also loaded. But you can see it says the system cannot find the file specified because it reached out to Microsoft. It tried to say, hey, WD filter is loaded in memory, and it reached out to the symbols server, and the symbol server says, no, I'm not going to give you the symbols for the EDR or the AV driver for Microsoft because it doesn't want us doing stuff that we're doing here. It publishes symbols for things like the kernel because you or me might run into a situation, or you might have developers and stuff that need to access the symbols to troubleshoot things. So it does publish those, but for things that are sensitive, like Windows Defender, the filter driver, and KSLD, that's for I think that's for our kernel driver here, or a KLDBG driver. That's actually for Windows Debugger because we're using a driver to debug the kernel. So anyways, forget it. You see EC2 WinUtil driver. Ooh, that would be a fun one to try to reverse. Oh, it's fun for later. Okay, but it is not this day. Okay, so yeah, these are all of the drivers and some of them that were not found. So we can just do LM. And this will list, like I was saying before, where it's downloaded the symbols. Those are referred to as PDB. And you can see these are all of the drivers that are just loaded by default. So you should see NT here. That's the actual kernel. So it's NTOS kernel, but it's just kind of symlinked, so to speak, to NT. And then you see HAL and different things that Lua, FV, some of these have, if you've done like your OSCP or something and you've compiled some kernel exploits, you might recognize some of these. So one would be Win32K has tons of kernel vulnerabilities over the years. what's the one that I'm looking for? It's escaping me. A starts with an A.
Run-DLL 42.
What was that?
Run-DLL 42.
Yeah, that's going to be a user mode one. A star. Nope. LMM A star. What is it? AFD. AFD.sys. That was a really big one. That was like used in all of like the pen testing classes. You know, for in the 2010s, basically, because it was like really reliable on Windows XP and Windows 2K3 and so forth. So that's just it's a networking driver basically, and there was a vulnerability in it that could be used fairly reliably, just natively with Windows. Anyways, okay, I'm getting off track. So you can do .cls. So we're just getting all of not only loading the symbol files, but it's showing the base addresses of each of these modules. And then whenever we reference a symbol, like if we were going to say, DQS, so that's display keywords with symbols. We're just dumping memory. Let's say NT PSP create process notify routine. So these are the callbacks for process creations. You don't have to worry about this. I'm just using it as an example. So the command we ran was DQS, which is display keywords. So display pointers essentially with symbols, which is going to kind of list it out like this, almost like a stack, so to speak, if you're used to, looking at Stack Overflows and stuff. And then NT is going to say that's the base address for the module that we're looking at. So it's going to resolve the base address, which is FFF, whatever that is. And then there's an offset PSP create process notify routine that's published in the symbols file. So it went out to Microsoft, it grabbed the symbol file, and there's an entry in the symbol file PSP create process notify routine for NT that gives us, I think it's the 1880, or maybe it's something like that. You can actually do this. We can do some quick calculations here with question mark, that minus NT, and we get 4D9880. And so take that address, subtract 4D9880, and you'll get the base address of the kernel. It's okay, this isn't like required information, it's just some context for working in the kernel debugger and so forth. Anyhow, something that we can do is search for kernel, they call it eProcess, or the structure in the kernel related to a process. And so whenever you create a process in user mode, the kernel is going to start the process and it's going to allocate a structure for with information related to that process. So we can search with bang process. Let's do 40. And what that's going to do is it's going to say, bang process is going to say search for the process with the PID4, exactly. And then 0 means we don't want a ton of information on it. It's just going to give us the quick info. Yep, so searching for process with CID equals 4. And then you see this address here, process, and that's the address of the structure in memory for the kernel or the system PID4 process. So what we can do is then display this structure and get all the information for it. And that's essentially what we're doing here. So find the eProcess for token, or sorry, excuse me, find the eProcess for system, and then we're going to copy its token. So that's kind of the idea is we're getting PID4, we're getting that kernel structure data, and then we're going to find the token for it so that we can copy and paste it into our, our own process, our exploit process, so to speak. So we can copy this, and then we're going to use the command or the command DT, and it's for display type. So we're going to display the structure with all of the members and all of the data and all of the values of that data. So we can do NT. So that's saying the structures from the NT symbols file, and then underscore eProcess. And if we do it without anything, it just shows essentially the function declaration. So this is pretty much mirrors what you would see if you were declaring it in your header file in C or C++. it's just going to get a bunch of extra data like the offsets and so forth. But it's pretty similar to what you would see in if you were going to try to reference the structure in C. This is a huge structure, relatively speaking. Usually, most structures are a lot smaller for the most part, but this is one of the bigger structures that you'll find and work with. And you can see things like, let's see, what am I looking for here? It's a good example. Flags, no, maybe not that one.
So it's like an API call table?
This is just, it's not for API calls per se. There's going to be addresses of things referenced here, but it's mostly just like, this is just an object in memory, essentially. Yeah, they call it structures, so to speak. But you can see right here, plus hex 358, the offset from the base of this structure is going to be the token. And so as long as you're on this version of Windows, if you find a process address or the address of a process structure in the kernel, and you get hex 358 from it, you're going to have the token. And so you read offset hex 358 from the base address of that process, you'll get a pointer. That pointer is going to be the pointer to the token. And assuming you found the PID4 one, that's going to be the system token. So what we can do here is actually append an address after this. So this was the address of we searched for PID4 in that process search that we originally did. And this is the address in the kernel. And then it will actually interpret all of the data and give you the values when you run that command. So if you give it an address, it will just kind of walk that structure at that address, essentially. Doesn't mean it's right. It just, you could do that to 0000 and it will give you whatever. And if it's not a paged address, it's going to give you garbage. But anyhow, if we go back to 358, which was the offset, you'll see this token. And if we click on it, we can dump the contents and we see a pointer here. And so that's the pointer to the system token. And so what we can do is actually, this is a fast reference. So a fast reference is a really, I mean, it's helpful, but when you're learning it, it's a little bit annoying because it's not what it seems to be. But what we can do is nt bang token. Just bear with me for a second, and I'll explain this. I did. Yes. Yeah. So I'm about to explain that. Yep. So this is the address. Well, with a caveat, this is the address of the token for the system process, which is what we found. And you noted that I missed an F. That was intentional because it's actually called a fast reference. So it's always going to be, I think, yeah, it's always going to be 8-bit aligned. I think that's how you would say that. So essentially, you clear out that last character, essentially, and just give it would be 290. Oh, 290. So you remove that F. So that last byte is called a reference counter. And so it's just a helpful thing in the kernel to give the kernel an understanding of how many references to that object there are in memory. So if it frees it, then it can know if it can free it. If it's anything other than 0, it knows that there's some reference to it with some other object. So if you free it, then something else could reference that freed data and then crash the system. So it's just kind of like a handy way to fix that or to address that issue. So to actually look at the actual data, we can dump the token information here. You can kind of ignore what I'm doing. And then this shows all of the information for the token. So we provided the pointer to the token, and we see all the data. The interesting thing here are like privileges. So we can just click on the privileges, and we see present and enabled. This doesn't mean anything to us as humans, but if we want a human representation of that, we can do bang token. And then this will show basically a who am I / all, or a who am I / priv that you might be familiar with, where you can see all the privileges like SE debug privilege and all of the sensitive ones that you would expect a system process to have. And so there's essentially a bitmap of all of that that it can reference to check like, oh, can you debug another process? It's going to check that privilege. Yes, you have that. Yes, you can do it. Excuse me. So I was running an exploit last night, and I had difficulty just copy and pasting the token because it was a heap overflow, and the particular primitive that I won't get into too much detail was writing too much data before what I wanted to write to. So it was corrupting the tokens. And so I had to find something that was safer to corrupt, so to speak. So I just went in here to my exploit process, and I just changed that from whatever it was to FFFFFF, essentially flipping every bit on, enabling every privilege. And so I was still running as my user, but I had modified the privileges that my process had. And so that was full privileges, and then I could do process injection into PID4. And so because you have SE debug privileges, that means that you can read and write to any process on the system. So you, even though you're not running a system, you can open up, get a handle to PID4, write data to it, shellcode, and then execute it and get system. So there's a lot of options available to us. Don't worry about that. It's just another example of some things that we can do.
How noisy from the EDR perspective?
I'm sorry?
How noisy it will be from the EDR perspective?
I love that question. That is a really good question. So token swapping, which is what we're doing now, is really noisy, because whenever you start something in the whenever you start a process, there's that address of functions that I mentioned, the callbacks. And so whenever a new process is started, it's going to walk that tree, or rather walk that list of processes. Sorry, callbacks. It's going to run each of those callbacks, one of which will be an EDR, and then the EDR will see a new process is created. It will track the token. Not every EDR. I'm speaking basically from CrowdStrike's perspective because I've done more testing with that. CrowdStrike will check the token. It will track it from the driver's perspective, and then if it sees a system token being swapped with the known kind of token that it started off with, then it will scream. Same thing with like impersonating a kernel thread, which we talked about before. It will also track, hey, this thread started as a user thread, and then it changed to a kernel thread. That's really suspicious, and so it'll throw all sorts of alerts, like this is likely an exploit process, something really malicious. So really great question. This I have not tried specifically, but it might be, I would assume that this would be a lot harder to detect. So if you want to be really slick, you could try doing something like that. Like, hey, I'm just going to find the bit for SE debug or something, and just flip that to on, and which is going to be a lot harder to kind of mitigate or detect. Present is pretty static. Enabled changes. So present is essentially the privileges that you have available to you, and then enabled is what you currently have enabled, and you can adjust the enabled. So for instance, you might have SE debug privilege present but not enabled, and then you have to enable it before you do something with that privilege. It's a little bit beyond the scope of our talk now, but what I mean is present shouldn't really change. So if an EDR tracks that present field, they could detect changes to that. Other things that you could do is modify security descriptors in the kernel. So you could go to PID4, find the security descriptor, and say, hey, not just administrators can, impact the system, but anybody can gain a handle to this process, and then you can just go in and process inject into it or something like that. So it's really, I would say it's really difficult to fully detect, every possible situation, but there are very common methods, like a few of which we've referenced tonight, that are, juicy targets for an attacker that an EDR can get some quick wins from. So yeah, sorry, I'm probably giving way too much information and spending way too much time, but hopefully that's kind of addressing some of the questions that they're great questions. So
Yeah, we probably should start to wrap up.
Yep. So the last thing.
If only for the reason that the batteries are going to die.
Yeah. All good. All good. So the last thing that we'll do is I'm just going to do who am I, and this is a little bit weird because I'm running as an administrator. So this would happen with any user. So I'm running as an administrator, but I'm not running a system or anything, right? So what we can do is we can do bang process 0, 0. If you give it 0, it's going to be a search, and we can just say cmd.exe to give us, we only have one cmd.exe running, which is the one I just started. So we can find this one and copy this and do dt nt bang eprocess there. And then instead of dumping the whole thing, we can just dump one member of that. And we can get our token here. And we can do the same thing just to look at that. Nt bang underscore token. If I learn how to type, just like I need to learn how to cloud. 0, and we could do that. You know, we can look at our privileges here, and we can see they're a lot different than the ones that, not that we're all, I mean, I don't even remember all the binary here, so just, it's different. But what we can do is a little bit easier way of seeing that is just doing bang token at that address, and this will give us more of the human readable stuff, which is very highly privileged because we're running in high integrity as an administrator, but so there's not much difference here. But if we were running in low privilege, this would work just fine too, because we're running in the kernel. So what we can do is play that again, and then if we go back up here, so this was the address of the PID4, so the system process. And so we can dump that. And then we can do EQ. So that's edit keyword. So we're going to edit memory in the kernel. So we're going to mimic what we would do in an exploit, just in this debugger here. So we can do EQ. Oh, 0. This is the value we want it to be. So that's the system token value from what's highlighted up there. And then if we go back up and we find the address of our cmd.exe process in the kernel, copy that, and then get the offset. So we're going to edit the keyword at the token offset from our cmd.exe process, and we're going to copy in the value of the token from the system process for PID4. Yeah, thank you. So that's this guy right here. So it's the offset. So if we didn't have that, that's what I did today when I was doing this beforehand. I crashed the system because I forgot to put the 358 there, and then when it tried to reference something on that process, it crashed. So we have to be very careful with the offsets that we're using. And we hit enter, and we go back here, and we're system. So that's essentially what we're doing. Yes. So whether it's shellcode or whether it's direct memory in the kernel, some people refer to this as DCOM or direct kernel object manipulation. So again, we're not using an exploit or shellcode. We're just mimicking what we're doing in WinDebug with a kernel exploit through like a buffer of read-write operations or whatever our vulnerability is. So
Usually you will use a driver to load your code.
yeah. So we would use a driver. So if it's a native kernel vulnerability, so like a vulnerability actually in the file system or something, you wouldn't need to load anything. But if it's like a fully patched system, you could bring, a vulnerable Dell driver or something that gives you this ability to just like read the token, copy it over, and then do this exact same thing with kernel telemetry. Like say, hey, here's the here is the this is slow. All the way up here. DQS NT PSP create process notify routine. So you would walk this one, resolve these references, find which one's pointing to your EDR driver, and then just remove it. And then it's not going to tell your EDR driver about new processes.
But now I have a different question. Let's say
Yeah.
you're already on an Xbox.
Yeah.
And you want to bring your driver, you still need to elevate yourself, and you still need to reboot the system.
Yes, that's a limitation. Exactly. Well, no, you don't need to reboot the system,
Right?
but you do need to elevate yourself. So to do this, you would need to reboot your system because we're in debug mode.
Load the driver.
To load the driver, you actually don't need to reboot. You just create a service with a type kernel pointing to the driver, and then start the service, and then it will load it into the kernel memory. Yeah. So you got to be careful though, because it will do the driver signature checks and so forth. So assuming you haven't.
The EDR is not saying that you have a new service running.
It will see that. Yeah, great question. It will see that. So there's a bunch of different ways that you can do that, and I won't share all of the tricks, but live on camera. But there are certain things you can do to be stealthier with that. What's that?
Can you give me access to the EDR?
If you want to, our ODPC course and our RTIC course are pretty reasonably priced, so you'll get an EDR lab with that. So. Yeah, we can talk about that later on. And we also do a lot of discounts, like 40% off and stuff like that. They're like $600 classes. They're really good. Lots and lots of information. Again, I didn't mean this to be marketing, but there are lots more of this kind of stuff. And if you want to wait, if you're paying it out of pocket, they're usually around holidays and stuff. Probably around 4th of July, we'll have another sale. If you're paying it through your company, please pay full price for our sake. Because unless you own the company, then. But no, I'm kidding. I don't really care. It's not going into my pocket anyway. So, anyways, yeah. So if you want some more of this kind of stuff, ODPC is probably what you want. That's our offensive development. We do a little bit more of it. There's a really great. If you want lots more of this, Sector 7 has a fantastic course. There's a user mode 1. Their advanced malware development 2 is all kernel driver stuff. It's more focused on EDR and so forth. But what's unique about our course is we give like 4 or 5 different EDRs, like Cortex and CrowdStrike. Well, we're actually removing CrowdStrike because we're getting cease and desist from them. So we don't want to be sued. So but there's other ones that you can use. But anyways, so thank you for bearing with all of my demos and my tangents and all of the bits and the bytes that we talked about. But hopefully this gives a little bit of context to what attackers are doing with bring your own vulnerable drivers, and can maybe pique some interest there. And if you ever want to talk about it more or talk about resources or exploits or anything like that, ping me. I'm on Discord, I'm on LinkedIn, I'm on Slack and stuff like that. So thanks a lot, guys. Please. Yeah, I guess I should have asked any questions. Go ahead.